Okay, this document links to the functions and equations topic of the Maths IB course, and it looks at getting students to develop algebraic connections between two quantities from a diagrammatical starting point. So as an example, on page 2.1, what we have is a unit circle. We have a point P that we can move around, and as I move the point P around, you can see that there is information being updated below it. The length of the opposite is being updated, and the angle XOP is being updated. Now on the left hand side we are going to try and plot the graph of angle XOP against the length of the opposite, and at the moment there's nothing on show. This allows students to look at the numbers and see if they can predict what the shape of the diagram might look like. When we choose to switch the graph on, you actually get a point now that's on show that represents the path that's being traced out, and students can check to see if their thoughts of the shape of the diagram will indeed on the right tracks. When students are confident enough to maybe generate the equation for the curve, they can simply pull up the graph entry line, type in what they think it is, and then the moment of satisfaction comes from as you continue to move the point P around, it hugs the graph. And so we have a nice visual confirmation that they have correctly derived the algebra for the connection between the angle XOP and the opposite. Now that's just one example of this type of activity. On page 3.1 we have a similar thing that generates the cosine graph. On page 4.1 we have a rectangle of 14 by 8, and within it we have a green parallelogram. And the task is to find out what is the connection between length D and the area. And again we can switch the graph on and off, and we can get students to recognize that there is a minimum of the area depending on the choice of D, and the challenge here obviously is for them to come up with some algebraic expression for them to type in. The thing to note here, even though we have D's on the diagram, we have to type in the expression in terms of X. The X coordinate is effectively my length D. So there could be a whole process gone through there, and you can type in the calculation in raw form if you wish. So if you were going to approach it by the direction of effectively doing the area of the whole rectangle and taking away all the different areas of the smaller triangles, for example, it would be X times 8 minus X for the small triangles which are currently on show, and then there would be X times 14 minus X for the other triangles, and we have to make sure that when we're typing these expressions in that we put a multiplication sign between all the brackets and we don't get it confused with functional notation, and we get the shape of a curve there. We can move the label out of the way, and again we can get the satisfaction of having correctly derived the algebra for the graph. If you wanted to simplify the algebra before you typed it in, you're perfectly welcome to. So these type activities continue onwards. There's another one there for the area of a triangle, where the starting constraining square is a 6 by 6. Same idea, can you come up with the algebra to go with it? And 6.1, a little bit more challenging, seeming a little bit less information, but the same task is there. When we get to page 7.1, we're looking at length AP versus length BP, and again they can try and predict what the shape of the graph would be and then switch it on and see if they were correct. There's no need for them to go about differentiating functions to find maximum minimums. The task here purely is generating the algebraic connection between the two quantities of interest, because that can then support their later work involving calculus. That's it. That's all it does.